April 3, 1897, Worcester, Massachusetts. The engineering specifications scattered across the American Tool Works conference table would have made the company's board of directors reach for their resignation letters. Chief designer Morton Hayes was proposing a lathe powered by leather belts and cone pulleys when every competitor was racing toward the future of geared transmissions. In the machine shop below, a prototype sat waiting for investor approval. Massive cast iron frame weighing 2,800 pounds for a machine bed measuring just 6 feet. No quick change gearbox, no modern speed selector, no electric motor mounting, just stepped cone pulleys that required manual belt shifting. Technology that belonged in Abraham Lincoln's America, not the dawn of the 20th century. Across the Atlantic, British manufacturers were showcasing back gear lathes with instant speed changes. German factories demonstrated precision screw-cutting machines that eliminated manual calculations. The Cincinnati Screw and Tap Company had just unveiled their revolutionary geared headstock that promised to make belt-driven equipment obsolete within 5 years. American Tool Works was investing $47,000 in development funds to build something every technical expert considered already outdated. The mathematics of industrial progress seemed brutally clear. Modern manufacturing demanded speed changes measured in seconds, not the minutes required for belt repositioning. Production efficiency required eliminating the skilled labor necessary to calculate cone pulley ratios. Quality control needed the consistency of gear-driven feeds rather than the variable tension of leather belts stretching and slipping under load. Hayes stood before skeptical investors holding blueprints that specified cast iron thickness 3 times heavier than industry standards. His lathe design called for bearing surfaces hand-scraped to tolerances no manufacturer bothered achieving anymore. The tailstock alone weighed more than entire competitor machines, built with redundancy that modern efficiency experts considered wasteful. The factory floor beyond the conference room revealed the scope of American manufacturing's transformation. Electric motors were replacing line shafts in progressive shops from Pennsylvania to Michigan. Overhead belt systems that had powered factories for 50 years were being dismantled as obsolete relics. The future belonged to self-contained machines with built-in power systems and rapid adjustment mechanisms that eliminated traditional machinist skills. Financial projections painted an even grimmer picture for Hayes's proposal. Geared lathes sold for $340 and required 2 days of delivery preparation. Hayes's conehead design would retail for $520 with 5 days of assembly and precision alignment necessary before shipping. The price premium assumed customers would pay extra for features that modern manufacturing philosophy considered unnecessary luxuries rather than practical advantages. Yet Hayes had calculated something that efficiency experts and modern engineers consistently overlooked. The geared lathes flooding the market were built to 1897 cost standards, using 1897 material quality under 1897 time pressures. His overbuilt relic was engineered for a lifespan that extended beyond anyone's reasonable planning horizon. 3,000 miles from American Tool Works, European machine shops were scrapping their 3rd generation of modern lathes, while colonial-era equipment continued operating in workshops too poor to afford replacement. The question Hayes posed was whether American manufacturing wanted machines that served quarterly earnings reports or tools that would outlast the companies that built them. The technical journals of celebrated a revolution in lathe manufacturing that promised unprecedented efficiency gains. Yet beneath the optimistic headlines, American machine shops were discovering that modern innovation came with costs that no one had calculated into the business projections. George Patterson managed production at the Cleveland Railway Car Works, where 6 new Cincinnati geared lathes had replaced aging belt-driven equipment just 14 months earlier. His maintenance logs told a story that contradicted every manufacturer's promise. Gear teeth showed measurable wear after 6 months of production work. The quick-change gearbox required lubrication every 48 hours to prevent seizure. 3 machines had experienced catastrophic gear failure, sending machinists scrambling as brass fragments showered across the workshop floor. The financial reality was even more troubling. Each geared lathe required replacement parts averaging $23 quarterly, costs that never appeared in the original purchase calculations. The gear assemblies, built with cost-efficient materials that kept retail prices competitive, simply could not withstand continuous industrial operation. Patterson calculated that within 5 years, his modern equipment would require complete gearbox replacements costing more than half the original machine price. Workshop conditions across American manufacturing revealed similar patterns that contradicted the promise of modern efficiency. The Westinghouse electric plant in Pittsburgh documented bearing failures on their new lathes every 7 to 9 months. The Baldwin Locomotive Works recorded alignment problems after 18 months, as lightweight castings warped under cutting stress. The Singer Manufacturing Company discovered that their quick-change mechanisms lost accuracy within 2 years, requiring expensive recalibration that older equipment never needed. The root cause extended beyond mechanical weakness into fundamental design philosophy. Modern lathes were engineered for contemporary manufacturing timelines where equipment depreciation calculated over 5 to 7 year lifespans. Cost efficiency demanded using minimum material thickness that satisfied immediate performance requirements. Competitive pricing required eliminating the hand-fitting and precision scraping that characterized traditional machine building. The entire industry had optimized for short-term economics rather than long-term durability. Machinist complaints intensified as the hidden costs of modern equipment became apparent through daily operation. Belt shifting on older lathes took 90 seconds but required no maintenance beyond annual belt replacement, costing $4. Quick change gearboxes saved 60 seconds per speed adjustment, but demanded constant lubrication, periodic inspection, and eventual complete replacement. The time savings disappeared into maintenance requirements that older technology never imposed. Production managers faced impossible calculations when planning equipment purchases. A new geared lathe at $340 seemed economical compared to older designs at $520. But 5-year operating costs, including maintenance, repairs, and early replacement, transformed the economics completely. The modern machines that promised efficiency were becoming expensive liabilities that absorbed capital through constant service requirements. The American Tool Works sales representatives heard these complaints daily as they attempted to sell Hayes's overbuilt conehead design into a market obsessed with modern features. Factory owners wanted quick-change capabilities that eliminated skilled labor. Production managers demanded electric motor integration that matched contemporary power systems. Purchasing departments required competitive pricing that made financial sense in annual budget reviews. Nobody wanted to invest premium dollars in proven technology when modern innovations promised revolutionary advances just over the horizon. Morton Hayes sat in his modest office overlooking the American Tool Works foundry, surrounded by rejected proposals that represented 3 years of fighting against inevitable industrial progress. At 52, he had spent 30 years building lathes, watching each generation of equipment become lighter, faster, and significantly less durable than the machines he had learned his craft producing. The rejection letters stacked on his desk told identical stories from different companies. The Pennsylvania Railroad declined his conehead proposal, citing preference for modern geared equipment with quick-change capabilities. The John Deere Works passed on his designs, noting that belt-driven lathes could not meet their production efficiency requirements. The Springfield Armory responded politely that government contracts now specified quick-change mechanisms as mandatory features for any machine tool purchase. Hayes pulled out the calculations that haunted his professional integrity. A modern geared lathe used cast-iron frames averaging 1.2 inches thick, adequate for immediate structural needs, insufficient for thermal stability over decades. His conehead design specified 3/8-inch frame thickness that provided mass dampening capable of absorbing vibration that would eventually destroy lighter construction. The weight penalty made his machines harder to install and impossible to relocate, disadvantages that purchasing agents considered deal breakers. The bearing specifications revealed even deeper philosophical divisions. Modern manufacturers achieved acceptable tolerances using bearings ground to 0.002-inch clearance, perfectly adequate for 5-year service life, completely inadequate for extended operation. Hayes insisted on hand-scraped bearing surfaces achieving 0.005-inch contact across the entire surface area. The labor cost alone added $40 to each machine's manufacturing expense for advantages that would not become apparent for decades. His design philosophy extended to components that modern engineers considered insignificant details. The cone pulleys were cast from close-grain iron rather than cheaper grades that satisfied immediate strength requirements. Each pulley received stress relief heat treatment that added 3 days to production schedules without improving initial performance. The tailstock castings underwent dimensional inspection after rough machining, after heat treatment, and again after final grinding, quality control that competitors abandoned as unnecessarily expensive. The fundamental conflict was between Hayes's experience building machines that lasted generations versus modern business reality demanding equipment that satisfied quarterly performance reviews. His lathe design assumed operators who understood mechanical principles and could perform minor adjustments. Contemporary manufacturing philosophy wanted machines that unskilled workers could operate without traditional machinist knowledge. The entire industrial world was moving away from the craft traditions that informed Hayes's engineering decisions. Financial pressure intensified as American Tool Works struggled to compete against manufacturers who optimized for modern market demands. The company's sales had declined 18% over 3 years as customers chose quick-change lathes from competitors who understood contemporary business requirements. Board members questioned Hayes's judgment, suggesting that attachment to outdated technology was destroying the company's future. Several directors openly advocated replacing him with younger engineers who embraced modern design philosophy rather than fighting against industrial progress. Yet Hayes possessed knowledge that came only through decades of repairing machines built across 50 years of lathe evolution. He had witnessed which design elements survived extended service and which innovations failed prematurely. That knowledge suggested building one more generation of overbuilt equipment before manufacturing completely abandoned the principles that created tools lasting beyond human lifetimes. The first 12 cone-head lathes shipped in November 1897 to customers who represented American manufacturing's most conservative segment. The Waterbury Clock Company ordered 2 machines specifically because their factory superintendent refused to trust geared lathes after 3 catastrophic failures in 18 months. The Pratt and Reed Piano Factory contracted for 1 lathe sized for their specialized ivory keywork that demanded precision modern equipment could not maintain. The New Haven Railroad shops purchased 3 machines for wheel-turning operations, where reliability mattered more than quick speed changes. These early adopters shared characteristics that separated them from mainstream manufacturing. Smaller operations where machine downtime directly impacted production capacity. Shops employing skilled machinists who understood traditional belt drive systems, companies willing to pay premium prices for equipment that would not require replacement within foreseeable planning horizons. The orders represented exactly the market segment that modern manufacturers dismissed as irrelevant to industrial progress. Thomas Brennan managed the machine shop at Waterbury Clock, where the first Hayes Conehead began operation on December 18, 1897. His daily logs documented performance that contradicted every assumption about belt-driven equipment in the modern era. The lathe handled brass, steel, and cast iron without the vibration issues that plagued their newer geared machines. Speed changes required manual belt shifting, but achieved cutting velocities that their quick-change lathes could not match without gear whine that signaled impending failure. Within 3 months, the performance difference became obvious enough that Waterbury ordered 4 additional machines. The conehead lathes required no maintenance beyond weekly oil application to expose bearing surfaces, a ritual that took 5 minutes compared to the daily lubrication demands of their geared equipment. Cutting accuracy remained consistent shift after shift without the gradual degradation that characterized modern machines as gear clearances increased with wear. The Pratt and Reed Piano Factory reported even more dramatic results. Their specialized ivory turning work demanded holding 0.001-inch tolerance across production runs, spanning weeks. Modern geared lathes lost this accuracy within days, as thermal cycling caused lightweight frames to warp microscopically. The Hayes Conehead maintained precision week after week, its massive cast iron structure providing thermal stability that no contemporary machine could achieve. Railroad shops discovered unexpected advantages in equipment that seemed primitive by modern standards. The cone pulley system that efficiency experts mocked actually provided infinite speed variation simply by adjusting belt position across the stepped cones. Geared quick-change mechanisms offered specific speeds but nothing between those fixed ratios. Skilled. Machinists could optimize cutting conditions with precision that quick-change mechanisms could not approach, assuming the machinist possessed knowledge that modern manufacturing was systematically eliminating. By April 1898, American Tool Works had orders for 47 conehead lathes from customers who valued durability over modern convenience. The success remained concentrated among smaller shops and conservative operations, exactly the market that mainstream manufacturers considered economically insignificant. Industry journals barely noticed equipment that represented regression to outdated technology rather than progress toward manufacturing's inevitable future. Yet the machines were accumulating operational hours without the maintenance crises that characterized modern equipment, statistics that would become significant only across timescales that exceeded anyone's business planning horizon. The 1899 Machine Tool Exposition in Chicago became the stage where American manufacturing's establishment delivered its verdict on Hayes's conehead design. The Cincinnati Screw and Tap Company's display featured their new Model 12 quick-change lathe with full electric motor integration, technology they positioned as the inevitable future. Their sales literature explicitly mocked belt-driven equipment as relics of the steam age, incompatible with modern electrical power systems revolutionizing American industry. James Wickham, chief engineer for the Brown and Sharp Manufacturing Company, delivered the keynote address that crystallized industry consensus against traditional lathe design. His presentation projected efficiency calculations proving that quick-change mechanisms saved 17 minutes per 8-hour shift compared to belt repositioning. Multiplied across a factory floor with 50 lathes, the time savings justified complete equipment replacement every 7 years. The mathematics demonstrated that modern geared lathes paid for themselves through efficiency gains even after accounting for maintenance costs and early replacement. The technical press enthusiastically amplified this message. Machinery magazine ran a feature article titled "The End of Belt Drive: Why Modern Manufacturing Demands Geared Transmission." The piece cited expert opinions from MIT's Mechanical Engineering Department explaining why cone pulleys represented fundamentally inferior technology. Variable speed control through mechanical gears provided precision that belt tension could never achieve. Electric motors required direct shaft connection impossible with traditional pulley systems. The entire concept of belt-driven machinery belonged to the 19th century that was disappearing into industrial history. American Tool Works faced increasingly hostile reception when their sales representatives attempted to sell conehead lathes to major manufacturers. The Westinghouse purchasing department rejected their proposal without evaluation, stating company policy prohibited purchasing non-geared equipment. The Baldwin Locomotive Works returned their quote with a note explaining they only considered lathes with quick change capability matching their production efficiency requirements. The Springfield Armory's procurement office specified that government contracts mandated modern features as minimum standards for any machine tool purchase. Financial analysts declared Hayes's design philosophy economically obsolete. A prominent Boston investment firm published research concluding that American Tool Works faced bankruptcy within 36 months unless they abandoned outdated product lines. The report cited declining market share as evidence that customers overwhelmingly preferred modern equipment regardless of durability advantages that took decades to materialize. Manufacturing efficiency demanded equipment replacement, down cycles measured in years, not the generation-spanning lifespans that heavy construction enabled. The mockery extended beyond business circles into technical education, reshaping American engineering. The newly established mechanical engineering programs at Cornell and MIT taught machine design principles that explicitly rejected overbuilding as wasteful. Modern engineering demanded calculating exact stress requirements and using minimum materials that satisfied those specifications. Hayes's practice of tripling frame thickness beyond calculated needs represented the imprecise methods of craftsmen rather than the scientific approach of trained engineers. Even among traditional machinists who appreciated belt-driven equipment, younger workers dismissed conehead lathes as unnecessary complexity. The rising generation had learned their trade on quick change machines where speed adjustments required moving a single lever. Belt shifting seemed like pointless skill investment when modern technology eliminated the need for such knowledge. The entire industrial culture was moving away from the craftsmanship traditions that informed Hayes's engineering decisions, leaving his cone head design isolated as an expensive anachronism in an industry racing toward the future. The story of Hayes's vindication unfolds not through dramatic demonstrations but through the patient accumulation of operational decades that no one in 1897 imagined witnessing. By 1925, the Waterbury Clock Company's original cone-head lathes had outlasted 3 complete generations of quick-change equipment. The maintenance logs that Thomas Brennan's successor maintained told a story invisible to contemporary observers. 28 years of continuous operation, total maintenance cost, $127 for bearing re-scraping performed once in 1913, plus routine oil and belt replacements, averaging $6 annually. The modern geared lathes purchased alongside them had been scrapped and replaced twice, each replacement costing more than the original conehead purchase price. The Pratt & Reed piano factory discovered something even more remarkable. Their 1,897 conehead maintained its original 0.001-inch accuracy into the 1,940 seconds without major rebuild. The massive cast iron frame that seemed wastefully heavy in 1897 provided thermal mass that absorbed decades of heat cycling without dimensional change. Modern lathes built with efficient material usage warped microscopically over years, requiring expensive realignment that eventually exceeded the economic value of the machine itself. World War II created the ultimate stress test when American manufacturing desperately needed every functional machine tool. The conehead lathes from Hayes's era ran 3-shift operations, producing critical components, while newer equipment failed under sustained loads. Military contractors who had mocked belt-driven technology in peacetime begged to purchase any surviving 1,897-era machines, discovering that overbuilt antiques outperformed modern precision equipment under wartime. Production demands. The post-war industrial boom revealed the full scope of Hayes's engineering prescience. Factories modernized with computer numerical control claimed efficiency gains that made traditional lathes obsolete. Yet those same factories maintained their 1,897 cone heads for operations requiring absolute reliability. The CNC machines produced higher volumes when functioning, but the ancient belt-driven equipment never stopped functioning, a distinction that became economically significant as semiconductor-controlled machines proved surprisingly fragile. By the 1,980 seconds, industrial archaeologists began documenting a phenomenon that contradicted everything modern manufacturing predicted. The 1,897 conehead lathes were still operating in shops across America. Many retained their original bearings. Some maintained micrometer-level precision after 90 years of service. The machines that industry experts declared obsolete in 1899 were outlasting equipment built with space-age materials and computer-aided design. The evidence became undeniable when metalworking museums discovered that their historical displays often functioned better than contemporary equipment in their restoration shops. A conehead lathe donated to the Smithsonian in 1972 as an industrial artifact was quietly returned to service when their modern Swiss-built precision lathe failed during a critical restoration project. The 75-year-old museum piece completed the work that state-of-the-art equipment could not handle reliably. The mathematical reality proved Hayes correct across timeframes that exceeded any reasonable business planning. A $520 lathe operating 100 years represented annual capital cost of $5.20 before maintenance. Modern machines at $340 lasting 7 years cost $48.57 annually, even without maintenance expenses. The overbuilt construction that seemed wastefully expensive in 1897 became extraordinarily economical when measured across the actual service life that massive cast iron frames enabled. Today, in 2024, more than a century after manufacturing experts declared conehead lathes obsolete, these machines continue operating in shops worldwide, a testament to engineering philosophy that modern efficiency calculations cannot capture. The Vermont repair shop, operated by Michael Chen, contains 3 1,897-era cone heads performing daily production work alongside CNC equipment costing $340,000 per machine. His maintenance logs document operational reality that defies contemporary manufacturing assumptions. The ancient lathes require bearing inspection every 5 years and periodic belt replacement. His modern CNC machines demand monthly calibration, annual controller updates, and complete spindle rebuilds every 8,000 operating hours. When critical components arrive requiring immediate turnaround, Chen uses the 7-year-old equipment because it never experiences the electronic failures that plague computer-controlled machinery. The precision instrument restoration industry has created an unexpected market for cone head lathes that their original manufacturers never anticipated. Watchmakers and scientific instrument specialists discovered that these ancient machines maintain accuracy levels that modern equipment rarely achieves. The massive castings provide vibration dampening impossible with contemporary lightweight construction. The belt drive system eliminates the electronic noise that interferes with precision measurement equipment. Features dismissed as primitive in 1897 have become premium advantages for specialized 21st-century applications. Engineering schools now study Hayes's designs as case studies in sustainable manufacturing, a concept that did not exist when he was fighting to build overbuilt equipment. MIT's Mechanical Engineering Department maintains 2 operational 1,897 cone heads to teach students about design philosophy that optimizes for lifetime cost rather than initial price. The machines demonstrate that minimizing material usage sometimes maximizes long-term expense through replacement cycles that occur within human career spans rather than across generations. The contrast with modern equipment remains stark. CNC lathes installed in 2010 are reaching end of service as electronic controllers become unsupported and mechanical components exceed economical repair costs. The manufacturers who built them have discontinued parts support, assuming equipment replacement rather than extended service. Meanwhile, the 1,897 cone heads continue operating with bearings that can be rescraped by any competent machinist using techniques that have not changed in 150 years. The industrial auction market reveals this value proposition in hard numbers. A well-maintained 1,897 cone head lathe now sells for $8,000 to $15,000, prices that reflect genuine production capability rather than antique collectability. Buyers are not museums preserving industrial history, but working shops needing reliable equipment for specialized operations. The machines that modern manufacturers mocked as worthless relics have become valuable tools commanding prices that exceed their original purchase cost after inflation adjustment. Morton Hayes died in 1923, never witnessing the full vindication of his engineering philosophy. He saw his cone head design survive into middle age but could not imagine its operational life extending past his grandchildren's generation. The machines he built to last indefinitely are approaching their 130th anniversary still performing precision metalwork, outlasting not just the quick change lathes that replaced them, but the CNC equipment that replaced those replacements, and the computer-controlled machines that represent contemporary manufacturing's cutting edge. The question his century-spanning legacy poses is whether modern industry's obsession with efficient material usage and rapid equipment replacement represents progress or simply expensive repetition of mistakes that 1,897 already solved.